It all started with a barely noticeable change, which went unnoticed by most. What was happening in the depths of our star gradually gained strength, causing concern among the few chosen ones who had enough knowledge to understand what was happening. It seemed that this solar cycle would be just like the previous ones, but something was different this time. At first, it manifested in small details, slight changes in the solar wind directions, more frequent flares on the star's surface. Then discussions began among those who monitored the sun's state, and there are few of them in the world. Speculations and hypotheses multiplied, but everyone understood that the problem might be more serious than anyone could have anticipated. No one could say with certainty what lay ahead, but intuition suggested that we should be prepared for the unexpected. Now, as the processes have become irreversible, scientists warn that the world might face something that has never happened before. No one wants to say it out loud, but the tension is rising. What does this mean for us, for our planet? And are we prepared for the consequences of the coming changes? If you found this deep dive into the mysteries of our star fascinating, make sure to hit that like button and subscribe to our channel. By doing so, you'll stay informed about the latest discoveries, cosmic phenomena, and stories that reveal the secrets of our universe. Let's explore the unknown together. Your support helps us keep shining a light on the wonders of space. The Sun, being an active and constantly changing star, undergoes regular cycles, one of which is the reversal of its magnetic field. The most well-known and studied is the 11-year solar cycle, sometimes referred to as the cycle of Chizhevsky. This process, occurring every 11 years, is associated with the dynamic interaction of plasma and magnetic fields in the solar corona, where energy continually flows. The Sun's magnetic field, which extends from its poles and forms the solar heliosphere, gradually weakens, changes polarity, and then strengthens again with the opposite polarity. There are also longer cycles of solar activity. For example, the Hale cycle, which lasts about 22 years, involves the global magnetic field of the Sun returning to its original state after 2 full 11-year cycles. In addition, there are much less pronounced longer cycles in solar activity, such as the Gleisberg cycle with a period of about 1 century, as well as super-long cycles lasting several thousand years. During the magnetic field inversion, the polarity of the northern and southern magnetic poles switches places. This process is not uncommon. It has occurred for billions of years and is driven by deep processes in the Sun's core and convective zone. However, despite its regularity, each magnetic field change comes with a series of consequences that affect not only the Sun, but the entire solar system, including our planet. Currently, according to NASA and other space agencies, the Sun is in its 25th solar cycle, which began in December 2019 and is expected to peak in 2025. During this period, the magnetic field inversion will be another significant event accompanied by an increase in solar activity. Signs of increased sunspot and flare activity are already being observed, indicating rising activity. Scientists report that in June 2023, there were more sunspots than in any other month of the current or previous 11-year solar cycle. Forecasts suggest that this cycle could be one of the most powerful in recent decades, drawing heightened attention from scientists. These events present certain challenges to humanity. On one hand, scientists have the opportunity to study the processes occurring on the Sun in detail and understand how they affect our planet. On the other hand, the risk of serious consequences for technological infrastructure and human health increases. Therefore, it is important not only to monitor developments, but also to prepare in advance for potential manifestations of solar activity that may accompany the upcoming solar magnetic field reversal. The inversion of the Sun's magnetic field has a significant impact on Earth's magnetosphere, which can, in turn, lead to changes in space weather and an increase in the number of geomagnetic storms. Earth's magnetosphere acts as a protective shield for our planet, reflecting charged particles from the solar wind and preventing them from reaching the surface. However, during periods of solar maximum activity, which accompanies the magnetic field reversal, the solar wind becomes significantly more powerful and energy-rich, potentially breaching the magnetosphere and causing severe geomagnetic storms. Geomagnetic storms are temporary disturbances in Earth's magnetic field caused by interactions between the solar wind and the magnetosphere. Depending on their strength, storms can have varying effects on our planet. Weak geomagnetic storms can produce auroras, beautiful light phenomena observable at polar latitudes. However, stronger storms can lead to serious consequences. The impact of the solar magnetic field inversion on Earth is linked to the fact that during this period, the solar wind can intensify and coronal mass ejections, CMEs, can become significantly more frequent. Coronal mass ejections, which are massive bursts of plasma and magnetic fields into space, can reach Earth and interact with its magnetosphere, causing powerful geomagnetic storms. According to the National Oceanic and Atmospheric Administration, NOAA, during periods of maximum solar activity, geomagnetic storms are classified by their intensity using the K-index, ranging from 2 to 9. The higher the K-index, the stronger the storm and its effects on people and technology. For example, on Monday, August 26th, there was solar activity with a K-index of 3, green level, indicating minor geomagnetic disturbances that do not affect human well-being. However, by Tuesday and Wednesday, August 27th and 28th, geomagnetic activity increased to a K-index of 4, yellow level, signifying a minor magnetic storm. Intense geomagnetic storms triggered by solar magnetic field reversals pose a serious threat to modern technologies upon which our daily lives depend. One of the main dangers is that powerful storms can disable satellites in Earth's orbit. These devices play a crucial role in providing communication, navigation, weather forecasting, and other critical services. But what would happen if these satellites were subjected to a powerful attack of charged particles during a peak in solar activity? During severe geomagnetic storms, charged particles from the solar wind can penetrate Earth's magnetosphere, creating conditions in orbit similar to radiation belts. This leads to increased radiation levels, which are hazardous to the electronic components of satellites. As a result, satellites may malfunction or experience operational disruptions. The most consequential storm of modern times, -589 nanotesla, occurred on March 13, 1989. At that time, the entire Canadian province of Quebec was without electricity for 12 hours. The infrastructure failed in less than 2 minutes. Some satellites lost contact with Earth for several hours, and there were equipment issues on the American Space Shuttle Discovery. In 1972, a powerful magnetic storm triggered widespread power and communication outages in the US, and in Vietnam, several sea mines with magnetic triggers set by American forces were activated. Another example is the storm that occurred in November 2003, during which many satellites experienced interruptions, and the Japanese Adios 2 sustained severe damage. Given that there are currently over 2,000 active satellites in Earth's orbit, can you imagine the scale of the problem if even more intense storms occur? Another vulnerable point is global positioning systems, GPS. GPS signals are transmitted via satellites and used in navigation systems ranging from automobiles to aviation and maritime transport. Disruptions in GPS functionality can lead to navigation failures, creating dangerous conditions for vehicles and people. On August 5, 2011, the amplitude of the magnetic field fluctuation increased from a Kp=2 level to a Kp=8 level within a few dozen minutes, according to a laboratory report, which resulted in significant GPS disruptions and temporary navigation issues for airlines. If such disruptions become more frequent and intense, how could this affect global transportation infrastructure and flight safety? During severe storms, Earth's ionosphere, which reflects radio waves, can undergo significant changes, leading to deterioration or complete cessation of shortwave radio communications. Powerful storms can induce electrical currents in long transmission lines, causing overloads and even transformer damage. If such an event occurred in a modern megacity, how long would it take to restore power, and what consequences could it have for the city's functioning? The solar magnetic field inversion, accompanied by increased solar activity, not only poses threats to technological infrastructure, but also carries risks to human health, especially for astronauts and airline passengers. During this period, the number of high-energy cosmic rays significantly increases, which can negatively impact living organisms outside Earth's protective atmosphere or at high altitudes. Cosmic rays are streams of high-energy particles primarily consisting of protons, alpha particles, and heavy element nuclei arriving in the solar system from deep space. Under the influence of solar activity and changes in the sun's magnetic field, the density and energy of these particles can increase substantially. Normally, Earth's magnetosphere and atmosphere effectively protect us from most cosmic rays. But at altitudes where airplanes fly or space stations are located, this shield is significantly weakened. Astronauts working on the International Space Station, ISS, or other orbital platforms are at increased risk from cosmic rays during periods of peak solar activity. The protection provided by the spacecraft's hull may not always fully block high-energy particles, and prolonged exposure can lead to radiation sickness, DNA damage, and an increased risk of cancer. During one of the previous solar activity cycles, scientists recorded increased radiation levels on the ISS to values that could be dangerous with prolonged exposure. How will modern space programs address this challenge? Airline passengers are also at risk, particularly those traveling at high altitudes and polar routes, where cosmic ray influence is strongest. Studies have shown that during periods of peak solar activity, the radiation dose received by passengers and crew can increase by 20 to 30% compared to normal conditions. Although these doses are usually low, repeated flights, especially among pilots and flight attendants, can increase the cumulative effect of radiation exposure. Every 1,000 years or so, an extreme solar eruption, like a spotlight into space, can significantly disrupt Earth's ozone layer and impact all life on the planet. This was warned in a recent study published in the journal PNAS, according to The Independent. Researchers, including those from the Swiss Federal Institute of Technology Zurich, noted that such an extreme solar particle event could expose people to high levels of harmful ultraviolet radiation, cause high cancer incidence, and lead to global climate changes. Researchers added that while modern solar flares are weak and easily deflected by Earth's magnetic field, extreme events have occurred in the past. Such an event could trigger a domino effect in Earth's ozone layer, disrupting its function for over a year. If the ozone layer is damaged, harmful ultraviolet radiation could reach Earth's surface, damaging the DNA of all forms of life. Researchers suspect that one of these extreme solar eruptions may have affected hunter-gatherer groups around 42,200 to 41,500 years ago, and likely contributed to the extinction of the last Neanderthals. The solar magnetic field inversion and related solar activity processes may present real health risks. It is crucial to take appropriate measures to minimize risks during solar maximum, both in orbit and on Earth. Observations of changes in the sun's magnetic field and its activity have become a priority for scientists and research centers worldwide. Both space-based and ground-based observatories equipped with advanced instruments are used to obtain highly accurate data on the state and behavior of our star. This data plays a crucial role in predicting potential impacts on Earth and its technological systems, especially in the context of the upcoming solar magnetic field inversion. One of the primary tools for observing the Sun is the Solar and Heliospheric Observatory, SOHO, which has been orbiting at the Lagrange point L1, about 1.5 million kilometers from Earth, since 1995. This spacecraft is equipped with spectrometers, coronagraphs, and other instruments that allow detailed studies of the solar corona, sunspots, and solar flares, as well as tracking solar wind streams. Data from SOHO are analyzed daily by scientists to monitor changes in the sun's magnetic field and predict possible bursts of activity. Another important data source is the Solar Terrestrial Relations Observatory, STEREO, consisting of 2 satellites launched on October 26, 2006, into heliocentric orbits close to Earth's orbit, one gradually trailing behind Earth, behind, and the other overtaking it, ahead. These satellites provide stereoscopic images of the Sun, enabling scientists to observe coronal mass ejections, CMEs, from different angles. which helps in more accurately predicting their trajectory and potential impact on Earth. During solar maximum, such observations become critically important for early warnings of possible geomagnetic storms. Ground-based observatories also play a vital role in monitoring solar activity. One of the most important is the National Solar Observatory, NSO, in the USA, which continuously monitors sunspots, prominences, and other phenomena. For example, the Daniel K. Inouye Solar Telescope, located on Maui, Hawaii, with its 4.24-meter off-axis Gregorian mirror, provides detailed images of the solar surface with a resolution of up to 20 kilometers, allowing for analysis of fine-scale magnetic field structures. The complexity of forecasting arises from the unpredictability of solar cycles. In 2009, during the solar minimum, scientists observed that the 24th solar cycle started later and was weaker than expected, raising questions about the upcoming 25th cycle, which began in December 2019. Preliminary forecasts based on observations suggest that this cycle could be more active than the previous one. However, precise parameters and peak activity are yet to be determined. An important development for science has been the implementation of numerical forecasting models based on observational data and plasma physics. These models help predict how the solar magnetic field inversion will affect space weather and Earth's magnetosphere. For example, the ENLIL model, developed by NOAA, simulates the propagation of solar emissions and their impact on Earth. Such forecasts provide crucial data for decision-making regarding technological infrastructure protection and public health. Despite significant progress, many questions remain. How accurately can we predict the intensity and timing of upcoming events? And how prepared are we for their potential consequences? The inversion of the sun's magnetic field is closely linked to solar activity, particularly solar spots, which are important indicators of the state of our star. Solar spots are regions with highly concentrated magnetic fields that appear darker than the surrounding surface due to their relatively lower temperature. These spots usually cluster in areas where the magnetic field is most intense, and their number peaks during solar maximum when the magnetic field inversion occurs. As the sun's magnetic field begins to reverse its polarity, there is a sharp increase in the number of solar spots. This process happens approximately every 11 years and is part of the solar cycle. During periods of maximum activity, the number of solar spots can reach several hundred. These spots can exist from a few days to several months, with sizes ranging from hundreds to tens of thousands of kilometers in diameter. Solar spots are not only visible manifestations of solar activity, but also play a key role in the formation of solar flares and coronal mass ejections, CMEs. These phenomena occur when the magnetic field in the area of the solar spots becomes unstable and releases a huge amount of energy in the form of flares and plasma ejections. Solar flares can reach energy levels equivalent to billions of megatons of TNT and are accompanied by radiation bursts that can reach Earth within minutes. There is a direct connection between the peak of solar spot activity and the frequency of solar flares and coronal mass ejections. Over the past few decades, scientists have carefully monitored this relationship, attempting to predict potential flares and ejections based on solar spot dynamics. It is important to note that not every group of solar spots leads to powerful flares or mass ejections, but their increase signals a higher probability of such events. The magnetic field inversion that occurs during solar maximum enhances instability processes in the solar corona, making the sun more active and unpredictable. For example, during the maximum of the 24th solar cycle, there was a sharp increase in X-class solar flares, the most powerful known, which can significantly impact space weather and Earth's magnetosphere. Are we prepared to face these challenges and minimize the potential risks they pose? Changes in the solar magnetic field associated with its reversal have broader implications than just affecting space weather or technological infrastructure. These processes can significantly impact Earth's climate and weather conditions, potentially increasing the frequency and intensity of extreme events. Although the influence of the sun on Earth's climate has been studied for decades, recent research indicates that changes in the sun's magnetic field might play a more significant role than previously thought. The reversal of the sun's magnetic field can affect atmospheric and oceanic circulation, causing changes in global climate systems. One example of such an impact is a shift in the distribution of heat and moisture in the atmosphere, which could lead to an increase in the frequency of extreme weather events such as hurricanes, floods, and droughts. For instance, studies have shown that during periods of increased solar activity, when magnetic field reversal occurs, there is a rise in the frequency of severe storms and other anomalous weather phenomena in various parts of the world. The effect known as space weather, a term that came into common use in the 1990s, is also of interest as it may influence atmospheric behavior and even its chemical composition. An increase in the flow of high-energy particles, particularly during periods of peak solar activity, can lead to changes in the upper layers of the atmosphere, including the ionosphere. These changes can affect radio wave transmission, which is important for navigation systems, and even impact ozone distribution, which in turn could influence the climate. However, the broader climatic effects caused by changes in the solar magnetic field are still under active study. The impact of solar activity on long-term climate changes, such as warming or cooling, remains a topic of debate within the scientific community. Some studies suggest a possible link between solar minima and periods of cooling, such as the Little Ice Age, which occurred in the 17th and 18th centuries when there was a decrease in sunspot activity. Nevertheless, other scientists emphasize that anthropogenic factors, such as greenhouse gas emissions, have a much more significant impact on contemporary climate processes than solar activity. To protect against potential threats related to the sun's magnetic field reversal, it is essential to take proactive measures now. Imagine a sudden solar flare causing a massive blackout, leaving millions of people without light and heat. To prevent this, governments and companies need to invest in monitoring systems and protective mechanisms that can avert such scenarios. But what if the preparation is insufficient? What are the consequences for the global economy, security, and everyday life? This involves not just technology, but life on Earth itself. While we cannot predict every move of the sun, we can be as prepared as possible for any scenario. Subscribe to the channel and stay updated on potential threats and ways to protect yourself.